Okay. In previous class, we did the concept of the electric field due to one charge. Okay. And before that, we did the concept of the electric field and alongside with the Coulomb's law and the rest of the things, right? Now, we have to discuss the graph of the electric field when you have the two unlike charges, right? So we know that previously we know that the unlike charges causes the electric field around themselves, right? And um, but the field pattern is such that it continue from one point to another point, and it it remain in every point inside in between the two charges, right? So if we try to make the resultant electric field, okay, we can see that the resultant electric field will not be zero at any point in between the two. Okay. I have yes. Okay, let me uh just okay. Okay, fine. So this is the two charge, and the electric field for one of the charge will decrease as you move away from it, and the electric field from the other charge will decrease as you move away, right? So one if you move away from the other charge, you will get closer to the other charge, so the effect of the other field will get stronger, okay, than the effect of the first field. Okay, now if we try to make sort of, by the way, the resultant electric field will not be zero in between the two things, right? So our graph should not go in the negative portion, right? Now, if we try to plot the values, so let's just imagine or assume that if the distance d in between the two charges, okay, equals to, and this is the electric field of the first one, okay, in Newton per Coulomb, okay, and this is the electric field of the other one in Newton per Coulomb, okay, and the distance is in centimeter, right? Now, I just want to put in some of the values, okay? And the values are going to be, actually, by the way, the distance is, let's say, varying like this, okay? So one, wait, 1, 2, 3, 4, 5, 6, 7, and 8, okay? So let's say 8 in between the two charges, the center to center, like the separation between the center to center we're talking about, okay? And this separation has a total distance, a total variation of 8 centimeter, right? If we consider the electric field value due to the first charge, I'm assuming it myself, I'm not calculating it. So let's say the field value decreases. mm, let's say initially, okay, so the first thing that I am assuming is both the charge are having the same magnitude, okay? Same magnitude of opposite charges, right? Mhm. So this is the first thing, right? The charges are of the same magnitude, right? So at the surface of both the spheres, the field value will be same, right? And as you move away from each of the mass, sorry, from each of the charge, then your field value will decrease according to the inverse square law. Okay. So let's say if the first value is 20, okay, 20, right? And either you can, okay, let's apply the inverse square law to get the values. Okay. So I'm assuming that the electric field for the first one is 20, right? And 20 divided by 4 gives you for the second one, and you add 2, okay, 5.0, right? Then 20 divided by 9 gives you the electric field for the third one, 2.2, okay? And then for the fourth one, 20 divided by 16, you'll get 1.3, okay? Then add 5 or add 25, you'll get 0.8, 0.8, okay? Then add 6, you'll get, sorry, 20 divided by 36, 36, you will get 0.56, 0.56, and then at at 749, you'll get 0.41, 0.41, okay, and then 8 is the last point. Then 8 is going to be 20 divided by 64, okay, 0.32, 0.31, okay. So what I'm doing over here is basically I'm just applying the inverse square law, right? I know that the electric field E1 R1 squared is equals to E2 R2 squared. We know that, right? And electric field for the first one is known. Okay, I put it here, right? And R for the first one is also known. Okay, I'm changing the value for the R2 and I'm getting the value of E for like E2, right? So when I put R2 as 2, so when I square it, get 4, and 20 divided by 4 gives me 5, then 3, C squared is 9, 9 divided by 20 gives me this, and so on, right? Is that clear? Now, the other one, the electric field for the other one, negative one, would be the opposite of this one, okay? Because if you consider the distance, if you consider the distance d from this point, okay, d is starting from this point and it's moving on, okay. So obviously at this point when you start for the other sphere, so at this point it will be the maximum value, right? So 0.31, 0.31, okay, and then 0.41, and then 0.56, and then 0.80, okay, and then 1.3, 2.2, 5.0, and 20, right? So I just switched the values, right? Because the value, the magnitude of the charges are same, right? But the distancing is basically done from making this positively charged as a reference, right? So when you're coming from the different end, so the value will be exactly flipped, okay? Now, if we try to draw, so you can see that the resultant electric field will be the subtraction of the two field, right? Because the electric field is a vector quantity and it changes, or the direction of the electric field is the direction of the electric field will change because of the charge. So your resultant electric field will also be different. So let's just first make the resultant electric field values, okay, and then we'll move on. Okay, so if I say that this is the E resultant, Okay, so, or a better word would be E net. Okay, so for the resultant electric field, you just need to subtract, right? Because if you imagine this charge, or if you imagine this charge, okay, so this the electric field due to the negative charge will attract this test charge toward this direction, and the electric field due to that will attract. Okay, so since they're in the same direction, so you don't have to subtract, you rather have to add. Okay, so it's just add the values and you'll get the final answer, right? So 20.31, 20.31, okay, and then 5.41, and then 0.22, 2.2 plus 0.56, okay, I'm getting 2.7676, okay, and then 1.9, okay, and then again 1.9, okay, and then 2.76, okay, and then 5.41, okay, and you'll have 20 point 20 point 20.31, right? So now these are the resultant electric field, okay, and if we try to make the graph by looking at the resultant electric field, you can also make the graph for the individual electric field as well as the resultant electric field, right? So but over here the resultant electric field is required, okay. Sometime in the paper they give you, or they ask you to find or to draw the resultant electric field graph as well, right? Like um they give you the graph for the individual electric field. You have to find the resultant like this, okay, by adding the points, okay, and then you have to solve for the resultant, or you have to draw the graph for the resultant electric field, right? So yep. Hmm, come on. Okay, that's done. Just to the other side, to the other side, and yep, fine. Okay, let's try to draw the graphs. Okay, the resultant graph would look like this. It go like this. Okay, like this. With a minimum point, if you look at the table, so the maximum value should start from 20, right? It should start from 20 for both of the graph, right? Because not 20, 20.31, 20.31, right? Because for both of the graph, okay, you have 20.31, okay, and the one is basically at the surface, okay. Okay, by the way, please keep in mind that the resultant electric field will be zero in did I mention it? Yes, the resultant electric field will be, or the electric field strength will be zero inside the sphere, okay, so there will be zero line which I have to make. So this is a 0 point, okay, okay, and this is a 0 point. Okay, I have to do a bit of the changing in the graph as well, a bit. Okay, instead of starting from the center, right? We can start from like somewhere in between. Okay, let me start. Let me start it with from this point to this point. Okay, okay, starting from this point. Okay, and ending at this point. Okay, okay, okay. So this is basically D, right? Okay. Is that clear? This is the D we are taking. Clear? This is D. Okay. And inside the sphere, we know that the electric field is zero, and at the sphere, where we count it as a one, okay, and then we move on. So this 1 to 8 is the distance between the spheres, right? Now, the starting values should be from 20.31, okay, for both of these stars, because we have the like charges and we have the same magnitude of charges, okay. And for this case, you should have the two graphs starting from the same value, right? Or electric field strength will be same if you have the same charge value. Okay. Now, the second thing is the minimum point. The minimum point should be in between the values, right? Okay. So it is like in between the values. Okay. So if we consider these 2 points, okay, so we have three reading to the right and three to the left. Okay. So this is like the point where the electric field is max minimum. Okay, and this will have a value of, okay, this will have the value of 1.9 according to the data. Okay, we have wrote, we have written. Okay, now and this is the minimum point, by the way, where the electron or where the proton experiences the least amount of electric force. Okay, but not zero. Okay, and yep, fine. So we can say that resultant field will be sum of E1 and E2, right? So resultant field is found by this at any point, right? And the individual graph would look like this. Individual graph for any positive or negative planet look like this, okay? Now, okay, so this is a concept for the two charges, okay? And by the way, if you draw the vector diagram, so the vector diagram would be one force is in this direction, okay? Which is F1, okay? And the other four would be in this direction, which would be F2, okay? And these two forces basically produce the resultant force when you add them to, because they both are in the same direction, okay. And we are also saying then same magnitude of charges, right? Yes, everyone, everything. Now let's move on to the another concept. Okay, over here we had the positive and negative opposite charges, right? Now we have the like charges, right? And for the like charges, the graph will be quite different. Okay, okay. You can also draw the data table for this one. Mm, if I just bring it a bit down. Okay. So let's say I am taking, okay. So let's say I am taking the D value, the distance value from this point, okay, this point to the other point. Okay. Now, this is the distance, by the way. Okay, and the distance increases from in any direction, right? We are taking the distance to the rightward direction as the increasing distance, right? So again, the distance increases. Okay, distance in centimeter increases. Okay, and 1, 2, 4, 5, and 7, and 8. Okay, these are the distances. Okay, so if I draw the electric field, or if I put in the values for the electric field, Newton per Coulomb. Okay, so electric field will going to, and I'm taking this as 20. Okay, so the rest will work. Okay, 20. And then okay, by the way, the electric field is, if you recall the formula, so electric field is equals to kq over r, right? So if you have the negative charge in your formula, then E would be negative. Okay, if you have the positive sign in your formula, then E would get positive. Okay, and due to that, the electric field will be negative or positive as well. Okay, now, so let's say the electric field is 20, then 5.5. I'm just picking up the values previously. Wait, let me just. Okay, that's it. And paste. Okay, this is the one. Newton per centimeter. Newton per coulomb. Okay, and to find the resultant, so E naught. E naught is basically the electric field, the resultant electric field. Okay, or you can say that E net. Okay, net electric field. Okay. Now, the net electric field will be due to the two charges, but you have to consider their direction as well. Okay, so one of the charge attract the small test charge in this direction, and the other force direction this direction. Okay, so when we try to make the graph, so the graph will move through the negative portion, right? So, and if you just try to subtract the values, right, because both the forces are in the different direction, so both the field will be in the different direction, and that is basically due to the charges. Okay, but since the field is given for you, so you just need to add or subtract them to get to the value. Okay, so now if we subtract 20 minus 0.31, I'm getting 19.69. Okay, then 5 minus 0.41. अच्छा, अगर कोई बच्चा इसका ऑपोजिट करे तो उससे भाई कोई फर्क नहीं पड़ता। ओके, 4.59. Okay, and then divided by, what were the radius you were using? Okay, just skip it. Okay, so if we subtract the two values, so 22.2 minus 0.56. 0.56. So it is 4.4. Okay, and then 1.3 minus zero point 0.8. It is 0.5. It is also 0.5. Okay, and that will going to be 0.56 plus 0.22. 2.2. So 2.76. And the second loss would be 0.41 minus 5. So I get 4.59. Ignore the negative sign. 4.59. Okay. And the last would be the same value as 19.69. 4.59. Okay. And then 4.4. How it come 4.4? 2.2 plus 0.56. 2.7. This should be 2.76. Okay. So now you can see that we have mm, 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 mm. Okay. If you consider any one as your negative value and the other one will as the positive one, so the graph would have the overall result in some direction. Okay. So let's say all of these values are positive. Let's say all of these values are negative. Okay. So the graph will start from positive, positive, and then positive, and then positive, and this gets negative. Okay. And then negative, negative, and negative, so on. Right. And this negativity and positivity is due to the electric charge. Okay, so now if you plot the graph like this, straight line, the electric field is maximum at the surface, and then zero at a far point. It should be, it should look like inverse square law. Okay, inverse square law has a very sharp slope initially. Okay, so yep, and then one. So this is how the graph should look like. Okay, okay, so this is how the graph should look like, and we don't require that. We can rather use this concept, right? Now, if we are interested in finding the resultant force value, so basically the resultant force will going to be the summation of the forces or all the forces that we have, okay, in the system. Okay. Now, if okay, so now if we have the resultant force in the opposite direction, okay, so the field should get zero at some point. This is something that we discussed. Okay. And then after that, if we try to make the equation, if we try to solve for the null point, so the solution for the null point would be like this. Okay. So let's imagine that this is the charge and this charge has two forces. One is attracting toward itself, right? And the other one is attracting toward itself, right? So F1 and F2, right? So if you write the resultant electric field, okay, resultant field, okay, it is basically E dot F. So E resultant is equals to E1 plus and then minus E2. Clear? E1 and E2, right? And I put the negative sign due to direction, I put the positive sign due to finding the resultant. Okay, resultant mean you are adding the two quantity, and due to the directional change you have to subtract. Now at a point where the resultant is 0, okay, this is the null point, by the way. This is the null point, by the way, and the null point is the point where the particle does not or the particle will not experiences any force. Okay, and it will move the way it is moving. Okay, but till the point where the next electric field started. Okay, now mm, this isn't it straight. Okay, so if the resultant electric field is 0, okay, if you are saying at null point, where do I- okay, so at null point the resultant field will be 0, right? The resultant field is 0. Okay, so you put E net is equals to 0, right? And this makes E1 equals E2. Okay, and then you can solve. The first one is, let's say, whether for that I have to give the value for D, or I have to give the another variable so that it will be more easier for us to understand, right? So now if we try to draw this graph, okay, using the same formulas, by the way, you can cancel the things out and you can give the ratio in the form of Q1 over QR as something, right? Which would be required in the question, right? So this is the constant for the net electric field we have. Okay, now mm, shall we just move on, or shall we keep the class to this point? Yes, any idea?
My second class started, so I think I have to leave.
Okay, you can leave.
Okay.
Okay,
I'll
that is, also ending the class. And we actually completed the electric field, non-uniform electric field till this point. We will do the electric field in the next portion, and alongside with electric potential. So I'll try to complete the chapter in the next week, and then we'll be done. Okay.
Okay.
That's it. Okay. Take care, guys. Love